Good. Good. What are we doing? So I've basically realized that the only way forward, which kind of a bit connects, but the ANSYS toolkit thing, the uncertain systems toolkit thing, and also the learning quantum mechanics stream of work or work stream a bit together is I kind of realized that the mistake that I made, in the current the current thing here, right, is that I ended up modeling, and I think I said that already. What I ended up doing is I ended up modeling a wave function as a hypergraph, which is not what you want to do. What I want to do is I want to model entanglement. I want to have I want to find a way to model entanglement, and I want to have a way to model the evolution of entanglement. Let's put it this way, which for which obviously I need to understand entanglement at its deepest depth, depths, deepest points. Um, and I kind of don't really know where to start. So I do have one reference, which is what the physics project does, which is not really so far deep, but maybe because I haven't found really the right resources. But I know that the way that the Wolfram team is modeling entanglement is as part of the multi-way graph. So basically, the ancestry of different states of different nodes is what models entanglement, right? But I want to put that aside for a second and see if I can model entanglement sort of as the primary model element, right? Like not a because what Wolfram is doing is the sort of you've got the instance, you've got the model level, you have a system, and at the multi-way level, you are modeling the evolution of the system, and it's at that second level where you kind of see entanglement evolve. And I want to see if I can just put that aside for a second and try to model entanglement and model a way for entanglement to evolve. And if I recall well, I think this was this text here. That's what we were working on in the previous stream. Yeah. Which is basically a saying, uh, yeah. So, but I think that that kind of table is not going to work anymore for what I want to do. And to be honest, I haven't fixed my digital pen, but maybe I can use Paint in a bit of a different way. So just to start getting some of my thoughts in the room. Um, JS Paint app. Mm, I mean, then I also found these. Like I've been Googling around how, like, what are existing ways to that entanglement is modeled because I think the wave function doesn't tell you this. It's a property. The entanglement is rather a property of the wave function, or it's something you can derive out of the wave function, right? You can try to take a wave function and ask the question, is this a state entangled? And then you do, SVD, or you do whatever factorization and try to find whether you can factor the qubits out and then, or express the wave function as a product of qubit states. And that would tell you that it's not entangled. But I'm looking for for a particular way to evolve the entanglement, right? And if so, let's try to put like black is qubit 1, red is qubit 2, right? And I'm not going to care about the specifics of the states now, but because maybe maybe I'm approaching these from the wrong perspective. But so this is qubit 3. So my current assumption, right, is that you can model entanglement with a hypergraph, because the way you would do this is you would model the entanglement as a hyperedge, so that the correlation between subsystems as a hyperedge, right? So that's my starting assumption. So regardless of what the correlation looks like, regardless of all this kind of stuff, you'd say, look, here, these two are entangled. Um, and then you can also say that these two are entangled. And my sense tells me this would be a way, right? To so this would be a way to specify, or this would be a way to model a bipartite entangled state, right? Where I think that is the right multipartite entanglement, but there was a bipartite, uh, the semi-separability exactly. No, the semi-separability. That's yeah, but that would be. Mm, no, no, no. That wouldn't be it. I think because in here you would have the three qubits entangled. Although, another question of interest would be whether um, can I just uh, can I go back? Whether so we'll just put some systems in here to just kind of have you know um, so I said my kind of question is like, is there a difference between modeling an entanglement, say like this, or saying that's all one hyperedge, right? So to me that would be intuitively a that would depict somehow that these three elements, these three qubits or subsystems are. I don't want to use the word maximally entangled, because I know that there for certain systems that is something you can't define, and that's defined around uh, the whole local transformation stuff and the whole resource theory of entanglement, and that is a bit, I think, can be a bit misleading. Uh, but then I don't know if this would be if these two would be equivalent. That is a question, right? Or if modeling this from that perspective would be something different, like would characterize a system type as a different type of entanglement within the system. Because that's where I think that I gain a bit more uh, expressibility when I actually don't talk about systems, but subsystems, but the states of the subsystems, the potential states subsystems are in. Say, we have the 0, 0 case and 1, 1, right? So this is qubit 0, this is qubit 1, and then you have like qubit 2 and qubit 3, and they're also like 0, 0 and 1, 1, right? So that's the case where you have 4 qubits, and the ones at the top are entangled. So that would be so in this kind of, that's what I was modeling before. In this kind of model, you would say you would rather put in hyperedges the state values that are correlated, right? So that tells you whenever qubit 0 is 0, we know that qubit 1 is 0, but we don't really know what qubit 2 and qubit 3 are doing. We know that they are in an apparently mixed state because they are entangled between each other, but we don't really know anything else about it. Mm, it's somewhat, that's the way that I used to do it before. It just, I ended up, I think, at some point making a misstep in modeling these as, that's a wave function, because now I don't know how to express, how to evolve these. Like, what if I now say want to apply a control NOT gate between qubits control NOT gate between qubits 1 and 2, right? And how do I do this? Do I effectively do I effectively put, like, one option would be that that would be equivalent to kind of put everything into another hyperedge, right? And then change these values. Because essentially, if I'm interacting, if I'm making, no, actually, not even that, right? I would need to put everything into a hyperedge. Because that essentially, what I'm saying is that the system Q1 and the system Q2, like I can't, they are now somewhat entangled, right? But by virtue of these, that's also not true. I should also include, you know, this part. That's what I'm struggling with. I don't really know what is an optimal way to model these, or whether what I should do is these, right? And then also these, right? So it's just that this one will become a 1, this one will become a 0. But then effectively, that will turn into a full, you merge that into one single hyperedge, and then you would need to copy the values in here, and then kind of have a similar thing like these, where where then these two things. So now, so essentially you would have now two hyperedges that say, let's say 0, 0, 0, 0, 1, 1, sort of. I think you would still keep these, right? But then everything is kind of wrapped up. That would be, God, this is this is so awful, probably. And then here I have 1, 1, right? 1, 0, 1, 1. Also keeping like this, and then boom, right? So you would still you would have something like this, because that still reflects the fact that if we know that qubit 1 it's got a 1, then we know that we are in this part of the model, but still we don't know completely anything about this other part, like the Q2 and Q3. Like, well, we know, sorry, that is a 0. Yeah, we still, you know, it's still like, let's say Quirk. Let's open up Quirk and see if we can do this. So I have a Hadamard gate, I have a control NOT gate, I have a Hadamard gate in here, another control NOT gate, right? So we have these, and now I add a control NOT here. And so if I say that Q1 mm, is a 1, let's say Q1 is here, I'll pause select on 1. So I know immediately that Q0 is 1, but then I kind of see that that state at the bottom is it stayed, being this kind of bell state with a 1001, which is really matching what I see here. Whereas if I would pause select for 0, I would see the 0011, which is kind of what I have here as well, right? So that seems to be a faithful representation of what would happen, right? But I have no idea because to be honest, one of the things that I wanted to do is I wanted to be able to model these with a rewrite system. But that's going to be a bit more complicated because there's a bit more, there's more things happening here. And if I now would say, run another CX gate to disentangle the thing, right? Because now qubits 1 and 2 share an edge, like they share an edge here, they share an edge here, right? There's no instance where they don't share an edge. So now I know that I can apply the rules independently within each hyperedge and say that is a 0 and that is another a 1 again. And here nothing happens. And now I should be able to realize that qubits 1 and 2, sorry, qubits 2 and 3, right, are the same here and the same here. So they are not entangled anymore because they are the same. This means I can take them away and then kind of go back to having the 0, 0 and the 1, 1. They're out of these, and then you kind of have the 0, 0 and the 1, 1 of the other two qubits separately, and so you've broken it. This seems to be a reasonable way to model these. Like, yeah, sure, like that kind of grows exponentially, but it almost feels like, so what would the CX rule look like for this to happen, right? Because that's not the only way to do that. There's another way to do that, which is, if that's my initial system, I could do it the other way around, right? I could just take this system and then duplicate this one, right? So this would be equivalent. So instead of these, right, which is Q1, Q2, no, 0 and 1, you would have Q0, Q1, and Q2, Q3. So you would have these. And these are equivalent. So how I know that, I don't know. But they should be equivalent because they tell you the same. Do they? Yeah, because if this means I'm going to have the same one mirrored down here. So if I say Q1 is post-selected by 1, I don't know in which one I am, so I'm kind of at both parts of the model. And then you still get back the same information, which is basically the fact that say Q2 and Q3 are in an apparently mixed state, right? Whereas if I ask here, okay, let's postulate Q2 for 0, I know that I'm in this part of the model, so I know that that's the state of Q0, Q1. And if I do that on the other side of the world, like on sort of my first approach to these, so there's the symmetry, right? Because here if I postulate Q2 for 0, then it could be this one, could be this one. So essentially, that thing somewhat collapses. So I think the postulation here would then collapse merge some of these hyperedges. But that seems to be a way to model these that doesn't require, but still, right? Still, that is to some extent just dealing with like two-party entanglement. It's just the subsystems can be understood as Q0, Q1 as one subsystem and Q2, Q3 as another subsystem. What if I would do that with the Toffoli gate? Let's do that, right? Discard. So what if I would say, look, what we're going to do is we're going to do this. How does the entanglement change? Let's try to follow the same approach, right? So we have a 0 and a 0, a 1 and a 1, and then we have a 0 and a 0, a 1 and a 1, and so this is, qubit 0, qubit 1, qubit 2, qubit 3. My handwriting is awesome. And now I have and these are like that, right? And now I have a CC knot, a Toffoli gate. How would I model these? Because now so you could do the same and say, look, for example, for the 1-1 case, we have now, this hyperedge, like that, right? But now I have a CC knot, and so before I just did one thing that now I realized might have been a mistake, which is that I would change, these to a 0 and these to a 1 because there's only one of these elements. But I'm biased because I'm kind of following an approach to the C naught where I kind of go more classically and say if the first, if it's a 1, then do that. But at the end of the day, that's not how you would represent a rule. The rule would just be find a pattern, right? And within these, like you'd still have hyper edges where these things are not shared. You have the one overarching. because this is so complicated. I don't know what would be the right way to approach this. Would I model it like one? So would I model it by what? Essentially, but just because this is just because the CC NOT gate, it has this kind of classical interpretation of like if this is one and this is one, then negate this one, right? But essentially, uh, you know, that's something that you could represent with a rule that does this, right? Turn it into 1, 1, 1, and then another rule that does turn it into the 1, 1, 0. And I know there's a really simplistic rule set, and ideally you want to have the not operation here somewhat embedded. Um, that's the that's what's damn complicated, and I don't know how to move on. It's frustrating. I would have to. I maybe would really have to understand more about how the entanglement stuff evolves, right? Saddle points of a conventional Feynman path integral are not entangled, since they comprise a sequence of classical field conversions. We combine insights from field theory and tensor networks by constructing a Feynman path integral over a sequence of matrix product states. The paths that determine the path integral include some degree of entanglement. This new feature allows several insights and applications. Phase transitions, the emergence of new classical collective variables in states that are not adiabatically continuous, with product states, features that are captured in product state field theories by proliferation of instantaneous. That is way too deep for me. I don't even understand the path integral yet completely. Um, Materials and technical, not the introduction. The technical documents. Launch documents, and then recent research. There's nothing about entanglement. There's no even easy way to search, is it? Is there? Here maybe. No, there's also no way to search through these. I'm a bit stuck, to be honest. How you would model that correctly? Um, you would merge, because essentially that's a Toffoli gate, right? So if I would start off with, like, say, a 0 plus 1, and maybe, maybe another 0 plus 1 and like a 0, so I would usually kind of separate that into, um, yeah, well, to be honest, that's the trick, right? That's what you gotta do. You gotta separate everything, like all these possible combinations, and then you've got these, and then these, and then these, and then this is the one that changes. So essentially, what I've done is I've combined the three affected qubits, but that is it's kind of cheating, because I know what the it is and it is not. I mean, it is the interpretation of a controlled operation at the end of the day, right? It's just that if I would have a scenario like this, then, well, there's only one way in which you can combine these, right? Which would be a 1 1 0 0 and a 1 1 1 1. So you kind of have this combination, right? And then say, oh look, only this case. So you keep combining the hyperedges until there's no and until all the qubits share the edges, and then it's when you can say, okay, now I can see the pattern, and so I can go and change this one to a 0, right? But I have essentially, what if we would just combine them by nesting? Not by combining, but by saying, look, um, sorry, like, look, um, you've got your guy here, and then you have this one and this one. So you're just doing like this one and this one, and now they share. Because okay, so the difference between these two models would be that here there so here all the so here qubits 1, 2, and 3, right? Um, they share a common hyper edge. No, wait a second. So the only ones that they don't share hyper edge would be in here, but when they don't share, they share the parent. Yeah, but that's true here as well. Okay, no, the I see. Okay, so So essentially, the rule would be here: you cannot have. So what is the difference? The difference here is that, like, man, I'm having such a problem. I have such a blurred mind right now. Um, you cannot have. They're sharing. They're not sharing. What the hell, man? So here, this is hyper H1, hyper H2, hyper H3. So here, okay, so one qubit. So qubit one, right, is in hyper edges 1 and say 0. That's hyper edge 0. Qubit 2 is in hyper edge 2 and hyper edge 0. And qubit 3 is in hyper edge 3 and hyper edge 0, right? Mm, the only difference here is that I need, what did I say? So it's in 3 and 0 and 2 and 0. Yeah. I need them to share. And here you have qubit 1, qubit 2, and qubit 3. Qubit 1 is, and let's say this is average A, B, C, and D. Or no, sorry. A is this one, B is this one. So here the qubit 1 is in hyperH 1 and hyperH A and in hyperH B. And also in hyperH. Okay, that's yet another hyperH. Uh, the what is the difference? The difference is they share all the hyperedges but one, right? Yeah, but that just feels too. That just feels not something that I can generalize upon. Here, they share also all but one. It almost feels like that's redundant. That's something that it's redundant because that we are already representing here that this is sort of a correlation and they all now already share one thing, and so it hopefully would be able to identify that this pattern 111 is inside hyper H0, and sure, there's also 101 and 100, right? Like I think the entanglement properties of that multi-control knot are already reflected by the addition of the E0, so of the hyper edge here, right? But then what's the difference between then what's the difference between what's the difference between the control node case and the control node case? Because effectively you would have the same hyperedge structure, right? It's just that now you would change these here for 0 versus in the other case you would change this here for a 0. Um, it's like you have multiple nodes, they all share a hyperedge. And so the thing is, if the hyperedges that they don't share internally impose any uh, constraint, whether they make whether they impose any constraint, because what I'm saying is that I know that if it's that is a 0, then I know that that's the value of Q3, so I still want to keep these. I feel that if I get rid of them, I lose information actually, which I don't want to. Still, the rule can apply because they share hyperedge. So the rules would say, cool, look for a hyperedge that is shared among nodes of the qubits that I'm mapping, right? And yeah, that could be something. That could be something. Okay, but then my claim here would be that my claim here would be that the kind of entanglement that you get is similar. And maybe what I should try to do is calculate an entanglement measure on these states and see um, if that agrees with the resource with the sort of the resource theory of entanglement. Okay, so that is one thing to prove. To try to prove. So I'd say check if the CX versus CCX result ends up with a same class of entanglement. Because whatever I model, I want to definitely make sure that it at least matches with the resource theory that it already exists, right? This means that the hyperedge structures should somewhat agree with what the resource is telling me, the resource theory of it, which is basically that these two types of entangled states are, equivalent from a resource perspective. Okay. That is at least one step forward towards what I was doing before, because it's before I think I was losing information because I was just merging these things. And now at least I keep this information and I say, look, there are these correlations, but now we're adding on top of that another correlation, which is these, right? Now, and essentially I have to double that because that's another question. Why am I doubling things? Why am I doing so the edge creation that groups the stuff makes kind of sense to me. The fact that I have to duplicate nodes makes sense to me as well, but only in a biased way because I know I'm in my head running the if that then that kind of interpretation of the control node, which it's not necessarily what one might want to do. But okay, it somewhat feels like that's a step forward. So the first part of a rewrite statement would do is take the map and just draw a hyperedge around it, because now we're going to group these stuff in there. Of course, that might be redundant in some cases. So you would only do that if you know that they are, if you know that they don't share all the hyperedges. Essentially, that's what I would have to check. So the rule the rule replacement would need to do step, say, 1, check if qubits share hyperedges, all hyperedges they're in. If not, create a new hyperedge, because that represents kind of the new. And if, don't know, maybe keep it, maybe check if these unentangles. I don't know, but that would be one step to modeling that. Because otherwise, I'm pretty much lost in terms of, you know, um, in terms of what else does something like the path integral or like the Schrodinger equation tell me about how entanglement is evolving. I'll have to do a bit more Googling around this. Anyway, I hope this was fun. And it's just really the first step in many to kind of, try to really understand entanglement better and see what the current theory tells me. And um, yeah, I don't know. It just I want to keep the learning quantum mechanics in focus here. So I should really probably pick up some resources on entanglement in general and try to understand that a bit more, in parallel to my efforts of modeling all this stuff. So anyway, have a good day.